Dear all, in this video we will be working on singular points and irregularity in singular points. So when we're doing series solutions, a lot of times we want to center around our solution around singular points, and it is important to understand what singular points are regular singular points so that we can work and do it, because irregular singular points we're not able to get a solution from that, but for regular singular points we can. So that's an important distinction we should be able to understand before we jump into those solutions. So to understand the singular points, we should consider a linear ordinary differential equation, such as y double prime plus pxy prime plus qxy equals to 0. It is important to put this in standard form because of the definition. And then we say that x sub 0 is an ordinary point if p of x of 0 and q of x of 0 are analytic. Otherwise, x0 is a singular point. So we should ask what analytic means. Well, in calculus, when we say analytic, what we mean is that the limit exists, we don't have a discontinuity. Alright, so you should think about this as an existing limit. Okay, if our limit is not existing, if we get some kind of asymptote, an infinite asymptote, in that case we would not be able to get a value. But other than that, every rational number, even irrational numbers, would be able to give us analytic results. So let's work on some examples. Our first example is y double prime plus 5xy prime plus 9y equals to 0. And this differential equation is already in standard form, so all we have to do is check our functions for p of x and q of x. So p of x will be equal to 5x, and q of x will be equal to 9. 5x is defined everywhere in the rational real number plane, so this doesn't have any discontinuity or any non-existing limits. Everywhere the limit exists. Likewise for 9, 9 is just a horizontal line on the plane, so 9 is also existing, and there's no problems with that too. So because of this, we don't have any singularity. No singularity. Okay, let's do number 2. Y double prime plus 1 over x y prime plus y equals to 0. This is also in standard form, and our p of x function will be 1 over x, and our q of x function will be equal to 1. Likewise to 9, 1 is also defined everywhere, and we don't have any discontinuity. However, for p of x equals to 1 over x, we do have a vertical asymptote at x equals to 0. You should already know that 1 over x does have a vertical asymptote at 0, but sometimes if you're not sure that if we have an asymptote or not, just try to get the limit from the right and the left doing calculus 1, and if you get different results for the limit, that will mean that the limit is not existing and we have a discontinuity there. So this is why we have a discontinuity at x equals 0. So at x equals 0, vertical asymptote. I'm just going to say vertical asymptote. Okay? And because of that, our singular point will be x0 equals 0. Well, a little further in this lecture, we will be focusing on regular and irregular singular points. But for now, just know that this is going to be a singular point. But further in the lecture, we will classify them as regular or irregular. Now let's keep going with these examples. We have p of x equals to 4 ln of x, and q of x equals to 8. Well, 8 is also defined everywhere. It's a constant number. However, 4 ln x is not defined everywhere. We don't have a definition when ln of x equals to 0. So we will say that x0 equals 0 is a singular point. Okay, singular point. And finally, let's do the next one, and we will have y double prime plus x squared y plus 4. Okay, and p of x will be equal to x squared, and x squared is defined everywhere, so this is not going to give us any singularity, but also q of x will be equal to 4, and 4 is also defined everywhere, so we don't have any singularity in this problem as well. Now let's work on the definition of the regular and irregular points, and based on this definition we will be solving some examples to understand the regular and irregular singular points. I'm just gonna write SPs for singular points. Okay. Point x0 is called a regular singular point if the factor x minus x0 appears at most to the first power in the denominator of p of x, and, this is an important word, and at most to the second power in the denominator of q of x. This is a regular singular point if these conditions are met. If either condition isn't met, x0 is an irregular singular point. This and means that both of them must be satisfied to satisfy the requirements for regular singular point. So I can understand if this definition feels confusing. It's not the most formal definition, but some examples will help us further understand what's going on. So let's start with doing some examples. Okay, so for this problem, we have a long second-order differential equation. The first thing we're going to do is quite obvious. We want to get the standard form. That's what we've been doing this entire course. So we will have 1 over x y prime plus 5 over x to the 5th y equals to 0. Okay, and now we should be able to see that x0 equals to 0 is automatically a singular point based on the last examples. Okay, well, is this a regular or irregular singular point? Now that's the question we have. Well, what did the definition tell us? If you want to go back, the x minus x0 term appears at most to the first power in the denominator of p of x. Well, what is p of x? 1 over x, and x0 is 0, so you can call this as 1 over x minus 0. And it appears to the first power. So at most, to the first power requirement is satisfied. And the second requirement also must be satisfied. At most, in the second power in the denominator of q of x. The q of x function is 5 over x to the 5th, which we can also write as 5 over x minus 0 to the 5th. And this is not the second power. It says that at most to the second power. So this is written in 5th power, and because one of the requirements were not met, we can just know that this is an irregular singular point. Okay, irregular SP. Okay, I'm just gonna say SP just to save some time. So let's work on this problem, shall we? Okay, so we want to start with simplifying this into the standard form. So I will just go ahead and write this in standard form. So we will have y double prime plus y divided by x times x plus 6 to the 6th power, x plus 6 to the 2nd power equals to 0. Okay, what is our p of x? Well, we don't have a p of x. So the factor in the p of x function is just going to be 0 because we have 0 over 1 p of x, right? And, you know, we can just say that the factor in the denominator is equal to 0. So we're not going to have any problems with the first requirement. See, it says for a regular point, it should appear at most to the first power. So we don't have any problems with that because we know that p of x is 0. Now, if we want to go find the singular points, the singular points will be x0 equals to 0, x0 can be equal to negative 6, And those are the only singular points we would have. Okay. And the second requirement tells us that in the q of x function, notice this is the q of x function. Q of x is equal to 1 over x times x plus 6 to the squared, x plus 6 squared. So it says that this factor at most to the second power in the denominator of q of x. Well, what is this at most to the second power? Yes. X plus 6 is squared, which is at most, which is still within that range of the requirements. And 1 over x. 1 over x is just the first power. So basically, both of these singular points are regular singular points. So we're going to say both. I'm just going to write both to make it clear. Both are regular SPs. Okay? Okay, now let's do this one. We have this differential equation, so we're just gonna write this in standard form. So y double prime plus x plus 2 y prime plus y equals to 0. Also, this should be divided by x squared minus 4 squared, and this is also divided by x squared minus 4 squared. Okay, and let me carry this equality a little like this. Okay, so this is our differential equation. Well, before we jump into the singular points, let's just make a little simplification with the q of x term, because there's nothing to simplify for q of x. So y double prime plus, so for the denominator, I want to write this as difference of two squares squared, so I'm just going to write x minus 2 squared times x plus 2 squared. Right? Can we do that? Yeah, sure, why not? This is just written as x minus 2 times x plus 2, and both of them are squared, so you can use some algebra to write it this way. Okay, so we're gonna have x plus 2 y prime, and we're just gonna cancel this x plus 2, so we're just gonna imagine we kind of cross this out, plus y over x squared minus 4 squared equals to 0. Okay, next step will be y double prime. I'm just gonna simplify this. X minus 2 squared, x plus 2, plus y over x squared minus 4 squared equals to 0. So what are the singular points? Well, singular points will be x0 equals to negative 2 is one of them. X0 equals to 2 is also one of them. Are both of these irregular or regular? So both of them are singular points. We know that because the denominator is going to have a vertical asymptote. However, notice this. We have 1 over x minus 2 squared. So x0 equals to 2 is actually not the greatest fit, not the best fit, because for the p of x function, our denominator's power exceeds 1. We don't want to have a more than 1, because remember what we defined. We said that up here, the point x0 is called a regular singular point if the factor x minus x0 appears at most to the first power in the denominator of p of x, which is why this one is just losing for that requirement to be a regular singular point. So x equals 2 is obviously definitely gonna be irregular. And about the x minus 2, the x0 equals to negative 2 factor, we can check that. The first p of x function has x plus 2, which is the first power. Okay, the first power, so that's why that's not going to be a problem. And for q of x, what we do have is we can just rewrite q of x, such as 1 over x minus 2, x squared minus 2, x squared plus 2, and both of them would be squared. Okay, so both of them are just, I'm sorry, this is not x squared, both of them are just x. Okay, so x minus 2 squared and x plus 2 squared, both of them don't appear more than the second power. So actually, this requirement is satisfied for both of the singular points, but the first part where we have 1 over x minus 2 squared is causing that reason why x0 equals to 2 is an irregular singular point. So this is why x0 equals to -2 will be a regular singular point.